Hello everyone, welcome back. In this video, we're going to start our study of calculus. Now there are two branches of calculus that we will cover in the course. One is called differential calculus, and the other is called integral calculus. Now differential calculus comes from trying to solve a certain problem, which is finding the equation of a line that is tangent to a curve. Now the method that is used to find the slope of the tangent line is the main idea behind differential calculus, and this method is called the derivative. Now we'll first define what secant and tangent lines are before we get into the problem of solving for the equation of a tangent line. So the word tangent is derived from the Latin word tangens, which means touching. So we define a tangent to a curve to be a line that touches a curve. Now a secant line, which is derived from the Latin word secans, means cutting. So it's a line that cuts a curve more than once. So here is an illustration of a tangent line and a secant line. So here we have the blue curve and the red line. Now the red line is tangent to this curve because it only touches the curve at a single point. Now over on the right, we have the same blue curve, but now we have a secant line because the secant line touches the curve at more than one point. So now let's think back to the original problem. What we want to find is the equation of a line that is tangent to a curve. Okay, so what we want to determine is the equation of this tangent line. Now recall that to find the equation of a line, what we need are two things. We need the slope of the line and any point that lies on the line. So now let's have a look at the secant line example here. So we are able to determine what the equation of the secant line is because we know 2 points which lies on this line. So these 2 points are also on the curve, so we are able to determine what the x and y coordinates of these 2 points are, and we can use the slope formula for these 2 points, and this will give us the slope of the line. So now we also know at least one of the points which lies on the line, so we can use either of these 2 points, and this will give us enough information to determine the equation of the secant line. Now if we look at the tangent line, we only know a single point which lies on this line. So now we have a look at the tangent line. We only have a single point which lies on the line. We do not have any other point on the line, so we are unable to determine what the slope of the tangent line is. So now the question is, how do we determine what the slope of the tangent line is? Well, what we could do is try to approximate the slope of the tangent line through the point by finding the slopes of the secant lines at other points along the curve. So let's have a look at the exercise here to approximate the slope of this tangent line. So recall that the slope of a line can be obtained by finding the rise over the run, which is the difference between the y coordinates, so y2 minus y1, over the difference in the x coordinates, which is x2 minus x1. So here our curve is given by x squared over 4, and we have the points P, which is 2, 1, and Q1, which is 4, 4. And we want to use these 2 points, which are on the curve, to approximate the slope of the tangent line at the point P. So let's find the slope of the line between these 2 points. So we can call the coordinates 4, 4 as our x2, y2, and our 2, 1 is x1, y1. So we can determine the slope of the tangent line. We have 4 minus 1 divided by 4 minus 2, which gives us 3 over 2. So the slope of the secant line between P and Q1 is 3 over 2. So now let's have a look at calculating the slope between P and Q2. So Q2 is the point 3, 9 over 4. So this is another point on the curve. And we can use this as our x2, y2. So if we were to determine the slope of the line between these 2 points, we would have 9 over 4 minus 1 over 3 minus 2. So let's make a common denominator in the numerator. We have 9 over 4 minus 4 over 4, and that's all divided by 1. Okay, so 9 over 4 minus 4 over 4 gives us 5 over 4. So the slope of the secant line through P and Q2 is 5 over 4. So let's have a look at an illustration of what we calculated. So here the blue curve is the function x squared over 4, and we were trying to figure out the slope of the tangent line at P by approximating it using the slopes of secant lines through Q1 and Q2. So we determined the slope of this purple line here to be 3 over 2, and we see that the slope of this line is an over approximation of the tangent line. Okay, so now we also determined the slope of the secant line between P and Q2, which is this green line here, and the slope of this line was 5 over 4. But this is still an over approximation of the tangent line. So how can we obtain a better approximation for the slope of this tangent line? Well, we could repeatedly choose our point Q to be closer and closer to P. And the closer Q is to P, then the better the approximation is to the tangent line. So how do we obtain a better approximation for the slope of the tangent line? Well, what we could do is choose the point Q to be closer and closer to P. And the closer the points Q is to P, then the better our approximation for the slope of the tangent line. And so what we want is to let the point Q approach P as close as possible, but not let it be equal to P. And this idea of letting the point Q approach P is called a limit. So we say that the slope of the tangent line is the limit of the slopes of the secant lines, and we can write this symbolically as follows. So the limit as Q approaching P for the slope of the secant line between P and Q is equal to the slope of the tangent line. And so if we let the point Q approach P and calculate the slope of the secant line, then this will give us the slope of the tangent line.